Okay. So when working with a limiting in this case, we would have sodium hydroxide would be the limiting reagent because we're dropping it into a number higher than what is normally needed. It's a one-to-one reaction. Now I use this little illustration right here to illustrate this, and what I'm going to do, so this is the base up here, NaOH, and down here we'll have the HCl. So when I put open the stopcock of the burette, and I'll drop one of the blue balls down into the red. And so what happens is one of the blues go away and the reds turn into salt. Now what I want you to notice here is that when that salt is formed, we still got a bunch of reds left over. When I dropped the blue in, it was overwhelmed by the excess of the red dots or the acid. In this case, the NaOH reacted with HCl and went to NaCl and H2O. So it was gone, but that stops the reaction. The reaction stops now. The red dots don't have anybody to react with. If I put another one in there, same thing will happen. You'll have so much acid higher than what you need. It'll react with just what it needs. And you can continue this until you completely consume all of the acid. Now, what I'm showing you here is an exact stoichiometric balance. That's the terminology that's used. In the reaction. But before we got to that point, the acid was in excess and the NaOH was in deficiency. As a result, the NaOH is used up and the reaction stops. So when we define the ideal limiting reagent, by definition, that component of a reaction mix which when consumed by reaction stops the chemical process. So you will always have an excess of the other component. The one that goes away first is the limiting reactant. Here's a simple example, starting with the same reaction. What we're going to do is add 2 moles of hydrochloric acid into 8 moles of sodium hydroxide, whatever. From the reaction, we know it's a 1-to-1 reaction ratio, meaning that for every mole of hydrochloric acid, I'm going to need 1 mole and only 1 mole of sodium hydroxide. Since I have 2 moles of hydrochloric acid, I'm only going to use 2 moles of sodium hydroxide. So I subtract out the amount I'm going to use. And this leaves us with 6 moles of NaOH in excess. Okay. Potassium superoxide is KO2, and it will react with water in the following. So in the reaction potassium superoxide, it'll react with water in this type and how much O2 moles will be formed. Here we have 0.25 moles in the problem. Well, the balanced equation has 4 in front of the KO2. So what I would come down here and I take 0.25 divided by 4. And that, so you get 0.0625 in that number. Then you take the water moles, 0.15 divided by 2, to get 0.075. See what I did? Coefficient divided by the given mole for each of the reactants. The smaller number is your limiting reagent. It says smaller number at the bottom. There we go. So you're only going to use, so you got a 4 to 2, that's 0.25, you're going to use half as much. 0.25 divided by 2. You're going to use half as much. But you started with 0.15, you only use 0.125, you got to have some extra. So that's what I'm talking about. That will be gone, completely gone out of the equation. The yield over here is a 4 to 3. So you can come in here and go 4 superoxide gives, and work only with the superoxide, the limiting reagent. 4 gives 3, then 0.25 gives X. Like that. And so 4X equals 3 times 0.25. X equals moles of the oxygen generated. So you get 0.187 down here. And okay, so we take lithium hydroxide, hydrobromic acid, and react them together, double replacement, and we make lithium bromide with water, the weak electrolyte being the driving force. Okay, I got 36 grams of lithium hydroxide. I'm going to put in 41 grams of hydrobromic acid. How much grams of lithium bromide are you going to use, and who's the limiting reagent? How much of the non-limiting reagent do you have left over? Okay. So we have 3 questions here that are very valid, very straightforward in terms of what they're asking for. I emphasize and teach convert to moles, solve the problems as needed, and then if they want something else at the end of the problem, convert back to the grams in this case. Okay? So we need to find the moles of lithium hydroxide. Okay, putting in some needed data, I calculated very quickly the formula weights of each one of the compounds, and I wrote them in over the equation that's given. So in terms of moles, lithium hydroxide is 36 over 24 mole of lithium hydroxide. Or 1.5 mole. The moles of hydrobromic acid is 41 divided by 81 is 0.506. The smaller one after you divide by the coefficients, limiting reagent. Now hear me, this is the component that you do all the rest of the problem with, because the other component is going to be left over in excess, right? That make sense? So this was going to be consumed, leaving excess lithium hydroxide. So any lithium bromide formed in the process is dependent on how much hydrobromic acid you put into the reaction. And that's a one-to-one issue. So since this is one-to-one, we're going to yield 0.506 mole of lithium bromide. And we used only 0.506 mole of the lithium hydroxide. And so we'll have an excess lithium hydroxide to be the difference in those two. .994 mole lithium hydroxide. So that's excess, you know, that's after the reaction stops. Now the question was, what is the mass generated? Well, if we worked it in moles like this, then all we have to do is multiply times 87 grams per mole. That equals 44 grams of lithium bromide generated in that problem. Okay. Theoretical and percent yield. The theoretical yield is the yield predicted from exact stoichiometric values. That is, if we have, say, we'll go back to the HCl plus NaOH goes to NaCl plus H2O. If I have 1 mole and 1 mole, I'm going to get 1 mole of sodium chloride. That's theoretical, based on the reactants put together. No matter how much of one or the other, or whether they're high or low, if I have 1 and then 40, all I'm going to use is 1. And it will predict, and this yield is a theoretical yield. Well, the problem with theoretical yield, that's in a perfect universe. And we never get the exact perfect yield. Actual yield is the laboratory results. What you get in the laboratory. Now we can predict the generation of 1 mole. If we have 1 mole here, no matter how much sodium hydroxide, but say the lab yield turned out to be 0.80 mole lithium, or sodium, when we're doing sodium chloride, okay, sodium chloride produced. This is the actual yield, or lab yield, however you want to say it. So when you calculate percent yield, it's percent of the actual yield divided by the theoretical yield times 100. So the percent yield in my example is the actual over the theoretical times 100%. In this case, 0.80 divided by 1.00 times 100%, of course 80% yield. So you're not going to get everything you predicted. Okay, the problems that you have to deal with on this will be twofold issues. One, you'll have to determine the limiting reagent and calculate the theoretical from that. Then the problem will give you the actual yield, and you'll calculate a percent yield. Okay? Okay. So you've got this right here. And you're putting 35 grams in an excess of O2, or you can specify so many grams of that. Well, how many grams of the SO2 are you going to generate? Well, the calculation from the equation in the ratios is called theoretical yield. So the first thing we need to do is convert to moles. Well, sulfur is 32 grams per mole. Look it up on the periodic table, divide into 35. So the moles of sulfur in this problem is 35 over 32 mole sulfur, 1.1 mole of sulfur. Well, it's a 1-to-1 reaction ratio, so this is going to be 1.10 mole of SO2 and 32.3. I have 96. This is 96 grams per mole right there. So I'm going to write 96 grams per mole. So my theoretical yield is 96 times 1.1 equals 105.6 grams. That's your theoretical. However, you go to the lab and you run this and you come out with 91.7 grams, which is your actual yield. You were expecting 105.6, but you only got 91.7. So the percent yield is actual over theoretical 100%, which is 91.7 over 105.6 times 100%. I think you're catching the trend. $86.8. Right there. Okay, this topic is stoichiometry of reactions in aqueous solution. It's working problems like this you still work toward the mole concept, but requires that you understand how to take solution data and convert it to moles based on the data that's given. The first thing you need to understand in here is the concentration term. Concentration of solute in a solution. And so concentration of solute is equal to the amount of solute in a specified volume of solution. And notice the denominator in that is two parts, which is solute and solvent. Now you won't have to deal with that issue, but just understand that we're talking about a solution, not an amount of solute in solvent. That's just a point of issue. One of the most widely used concentration terms, and I'm sure you've recognized this, is a concept called molarity. Capital M is the term. A molar solution is defined as the moles of solute divided by the volume of solution expressed in liters. Like that. If I wanted to prepare a 1 molar sodium chloride solution, I would dissolve 1 mole NaCl solid. I would dissolve 1 mole of sodium chloride salt, which is 58 grams, okay, in enough solvent, in this case water, to make 1.000 liter total volume of solution. Okay. Solution data applied to equation stoichiometry. If you look at the expression or the definition of molarity, this is moles over volume expressed in liters. Well, I can solve that for moles, the numerator here, from the definition of molarity. And moles is equal to molarity of the solution you're working with times the volume in liters of the solution you're interested in. Okay? So to work with chemical reactions in solution, aqueous solution, you'll be given, say, a molarity volume. Well, you take that those numbers and convert to moles and apply it to the equation. Okay? Now I'll set up a problem and show you how it's done. See the top? You already know how to work with that. It's 1-to-1 ratios, right, all the way across. Now, how do you take that 25 milliliters of 0.15 molar HCl and pour it in with 30 milliliters of 0.11 molar sodium hydroxide? Who's the limiting reagent? And how much is left over after the reaction is completed? Convert to moles. Apply to the equation. One in the least amount, since it's 1-to-1. Least amount is your limiting reagent, and another one's in excess. Okay? Let's see what we're talking about. Okay? This we need to convert to moles. Well, moles is equal to molarity times volume expressed in liters. So if I'm given 25 milliliters of 0.15 molar HCl plus 30 milliliters. Now watch how I set this up. It works real well. Molar NaOH. I want to convert that to moles. Now watch me close on this. This is a real learning element here. That has to be in liters. If you're in milliliters, move the decimal 3 places to the left. I'll put it up there. So I'll move that over 3 places to the left. I'm going to have 0.025 liters. But I'm not going to put liters on it. I'm just going to put 0.025. And then I'm going to put 0.15 and mole HCl. See what I did? Molarity. Excuse me. Plus, now do the same thing with this one. 0.030 times 0.11 mole of sodium hydroxide. See how I took the data of here and kind of rewrote it, but in context where I can immediately see through the calculation. Molarity times volume. So in this, okay, so when we multiply these two together, this is what we get. Molarity times volume in liters gives you moles. Is when I find the limiting reagent and identify it, I come over here and subtract is used. Okay, see, if this is a limiting reagent, it's gone. Ain't no more. And so we take the difference in those two, and this is what's in excess, mole-wise. Now, you need to define the concentration of the excess. This is in moles. And listen, moles ain't molarity. Molarity is moles over liters. Molarity of HCl aqueous solution is moles of HCl, which is this number right here, divided by solution mix. Total solution mix. Okay? And so I'll take 0.0 in liters. Put liters down there. 0.0045 mole of HCl divided by, we mixed 25 and 30. So 25 and 30, 55 milliliters, which is of course 0.055 liters. So 0.055 liters, see that's moles per liter now. And so after you do the mix, you'll have a molarity, an acid molarity, (0.0082 molar solution in HCl. And if you want the pH of that excess, is minus log of the hydronium ion concentration, minus log of 0.0082, right there. And just punch a log button when you get that far, and you have a 2.1 pH on the solution after you mix everything together.